The rules of resonance. So, and actually I'm going to backtrack here real quickly. When we looked at resonance in general chemistry and through our Lewis structure rules, it was nice kind of in Gen Chem because if you follow the way that I've told you to draw Lewis structures, the resonance kind of falls out of it because you end up with a situation where an atom hasn't achieved its octet. You just have to move electrons towards it. There was multiple places to move electrons from. You have resonance. Done. Right? Organic chemistry is similar, except that very typically what happens is what we end up with, is a structure. Okay? You aren't being asked to go from the formula to the structure. We start with a structure. Primary reason being, if I gave you the formula, C6H6, there's probably a few different structures you could have come up with that would have matched that formula. Virtually none of them would have had the same chemistry. Okay? So instead of looking at formulas, we need to look at structures. Okay? So almost always you will be seeing those structures pop up. So it's then how do we manipulate those structures to find resonance, because that's the next hardest part. Is that going this way? Oh, you just need, okay. Never mind. Oh, okay. So once we're given a structure, how do we manipulate resonance? So rule number 1, find a source of electrons. Okay. How do we know we have electrons?
Bonds.
Bonds. A line, a bond, represents electrons. How else do we know we have electrons? Lone pairs, those little dots. Guess what the dot represented? An electron. So we're just trying to find a source of electrons and then see if we can move it. Okay, the see if we can move it limits the type of electrons we're allowed to move. Okay, so in parentheses, we can only move, unfortunately we're calling it this, multi-bonds or non-bonding pairs of electrons or single electrons. Okay? You won't be seeing single electrons for a while, so you don't have to panic about that one. But the multiple bonds and the lone pairs are both valid electrons to move. The lone pairs or the non-bonding pairs of electrons should be familiar from general chemistry. The one that becomes a little bit more challenging is the multi-bond. Okay? We can't move single bonds. Single bonds aren't allowed to be moved because if I move them, let's go down to that structure. Let's pick this single bond, our red one, and I want to move those electrons. Let's say we move them here. Do I have a bond anymore? No. Do I have the same structure? No. I now have 2 pieces instead of 1 piece. So that is not a valid resonance move because the whole point of resonance is that I don't change the structure. Could I have moved the electrons here? Again, no. The bond is now no longer present and I have 2 pieces again. Okay? So single bonds you can't touch. Okay? They lock the structure in that position and in that place. If we touch them, we destroy our structure. Okay? What about multi-bonds? Okay? So a multi-bond would include double or triple bonds. Okay? So let's pick a double bond. What if I take one line in the multiple bond and I move that one line? Okay? Let's say we move it here. What is the result of that? Did I change anything else in the structure? No, so everything else must get redrawn. Those are saying, well, isn't that repetitive? Yes. Get used to it. Okay. Draw, draw. What did we do with those electrons? We put them on the carbon. Okay, and that can get tricky, but notice where the arrow is pointing. It's pointing directly at that point, which is defined as a carbon. I know it can be a tricky statement. Whoops. So it has a lone pair of electrons. The last step in Lewis structure is to do what? Formal charge. So we now go through and look at each of the atoms within our structure and apply a formal charge, and we would find the one with the lone pair has a negative charge, and the one that lost the pi or the double bond is positive. And we now have a new Lewis structure. Did I break any of the single bonds? No. So the atom connectivity is really the same. All I've done is moved some electrons around that didn't change the structure. Okay? That is, by definition, resonance. Okay? That's the point. So to do that, our first thing was find electrons. The next part was move those electrons. Because electrons are inherently unstable, we can only move them within the immediate vicinity. Okay? So our rules for immediate vicinity is if we start at a bond, we can only move it to an atom. Okay? So if I started at that bond, could I move them to that atom? Why not? It's not in the vicinity. It's too far away. We can only move the electrons to the atoms immediately next to it. Okay, well, how about to that atom? That one's closer, isn't it?
Yes.
It's still not right next to it. I can only move it to the atom immediately connected to it. Okay? The other option is if I had electrons on an atom, I can move them immediately to a bond, and only to a bond. I can't go to another atom. I can only go to a bond. And those are the two rules that when we looked at resonance at first, we said we're allowed to do. And that was it. Okay? Step 3, verify that our octets are satisfied. Okay? If there's too few electrons, then we would go back and repeat step 2. Okay? By finding more electrons and shifting electrons around. If there's too many electrons, we would break another multiple bond. Okay? By moving electrons. How? If I have too many electrons, I would break a multiple bond by moving electrons from a bond to an atom, because I'm by definition starting at that multiple bond. So I can only take them from that bond to the atom. So we're still reusing the rules on how we move electrons. In all cases, we are always starting with our electrons, and we're showing where those electrons move to. That's the point of the arrow. We're not showing how atoms move, because in resonance, what do the atoms do? They lock. They stay exactly where they're located. We're never moving an atom. Okay? So what we've done is moved electrons. We've generated a new structure. We could then go back and evaluate our octet. If there's too few electrons, we can repeat step 2. Do we need to worry about that one for this resonance structure? For people that have talked to me about it, they might be saying no, but I kind of conveniently ignored one part. How many electrons around our negatively charged carbon? There's 2, 4, 6, 7, 8. There's 8 electrons. Well, that's an octet. That was silly, Mike. Why'd you point that out? What's right next to it? A carbon with a positive charge that has 2, 4, 6 electrons around it. So it is technically missing its octet. Okay? Because we started with a neutral structure, when we broke that bond, we are generating charge, and what we are inherently drawing is a bad structure, because we have generated said charge. Okay? Before we freak out and ignore it, we do want to realize that that structure does have some valid uses to it. First and foremost, I now have an idea of how that molecule can react. With the very first structure, where's the positive atom? You don't see one. But when I draw a resonance structure, what do I see? A positive atom. I now have a site of potential reactivity, okay, that I could manipulate by just drawing a bad form of a resonance structure. Okay, but let's see what we could do with this. Okay. What do you think is the most reactive thing in here? That's kind of a loaded question, and I think I'm going to get the answer I don't want. But let's try. What's the most reactive thing in this structure? Electrons. Thank you. I like that. Let's work with that. Let's ignore everything else. Lone pair of electrons. Those are reactive. Okay. What I'm trying to do is to stabilize them. So what should I try and do with electrons? Move them. How about we move them according to our rules of resonance? How could I move those electrons? Okay. I could move them right back. That's awesome. What does that mean? I reversed what I just did. Okay, is that valid? Yes. Is that exciting? No. So let's not do that. Whoa, that was a really big eraser. Where else could I potentially move those electrons? Okay. I now have electrons on an atom. I can move them to a bond. We checked one bond to the left. Are there other bonds that I could move those to? Where's that other bond? I accept to the right. I'm going to stick with that. To the right, I've got a bond right there. What would be the result of that? A double bond where? To that hydrogen. This move in and of itself is not a problem. What becomes problematic is, does it result in a valid structure? No. So I've attempted a move, and I now need to decide, can I satisfy it or make it better by adjusting one of these other things? Okay. Well, what's the issue? What's the problem with that structure as drawn? And pretend the same as all of them. Hydrogen has too many electrons. So I'm not in the too few electrons, I'm in the too many electrons. If I'm in the too many electrons, what I will do is break a multiple bond. Okay. Well, the hydrogen's the problem. Does it have a multiple bond? Yes. Where's that multiple bond? Right there. Okay. So that's a problem. I need to satisfy it. But I can't do it to this structure because the purple structure doesn't exist. That was an invalid thing. So what I'm doing is saying, I moved, oop, that was a problem, so I'm going to go back and say, okay, I'll add another arrow to fix that. Okay. Well, where were those electrons coming from? Well, the space between the carbon and the hydrogen. So right in there, right? So I would add a second arrow. What's the result? I go back to exactly where I was. The issue is not that we've drawn an arrow and then said, oh, everything's horrible and now life has failed. It's the evaluation of, did that work? That didn't work, which means try something else. That's okay. Okay? And one of the things that I think people get afraid about is to draw the wrong thing. Okay? Let me...
That it didn't work, it just went back to the...
So when we moved that arrow, what happened? Did we generate a structure that worked?
No.
No. Okay? So to fix it, what did we do?
Move it back.
We moved it right back, which then meant nothing happened. Okay? So the action of drawing that first arrow resulted in a structure that was invalid. Okay? And everybody tends to panic and go, oh my God, I drew something wrong and now life is miserable. Okay? Let's put it in another way. If you draw something right in this class, you're probably doing something wrong. Okay? Yeah, process that one a little bit. Okay? You probably lucked yourself into it because you don't have the experience yet. Once you have the experience, then yes, you can be consistently drawing things right. But at this stage, you will be drawing it wrong. Don't panic. Leave it there. Learn from it. Change and adapt. Okay? So in this case, I have to change and adapt by erasing everything because I don't have enough space. You have lots of paper. If you need help with that paper, let me know. I will give you some. Okay? So we checked moving the electrons to the left, took us backwards. Checked moving the electrons to the hydrogen, and it took us in circles. Do I have any other place that I can move those electrons? I can move it to the bond down. What happens when I do that? So I will again test. I want to see what the result of that arrow does. Where is everything? Positive, double. Sorry. Right? Is there a problem with that structure?
Yeah.
That carbon exceeds the octet. Okay, so that goes back to rule 3. If too many electrons, I need to break a multiple bond, just like we did with the hydrogen. Okay, so we're now looking at an invalid structure and saying, to make this valid, I have to change something on the red structure. Okay, I have to add a new arrow. That arrow could just as easily be going from that position where we just formed a new bond and take it right back. Is that exciting? No. That would mean there is no resonance and we're done. Okay. Do I have another multiple bond at that carbon? Yeah. So what should I do? Well, move it. How do I want to move it? Well, I'll move it according to the two rules that we currently have. Since I'm at a bond, I can only move it to an atom. The only atom I could move it to, well, there's two I can move it to. I can move it to the blue circle one or the bottom. Which one do I move that? Why the bottom? Why do I not move it to the blue one? The issue was that that atom exceeded its octet. If we moved the electrons to it, all we did was, at best, make it worse, okay, by giving it even more electrons. Okay, and at worst, I said that wrong. Either way, it didn't work. Okay, so we added our second arrow. So because this structure was invalid, we'll now erase it, and we will draw the new result of our arrow pushing. What is the new result of our arrow pushing? I've gotten in a whistling mood lately. Sorry. Positive, right?
Yeah. But isn't there...
All right. That's it. To go from the black structure to the purple structure, in the very first step, I went from a bond to an atom. That was one of my rules. To go from the red to the purple, I went from an atom to a bond. That's one of my rules. And I also went from a bond to an atom in the same step. Am I allowed multiple arrows in the same step? Absolutely. Okay? As long as they are all feasible to happen, which deals with mechanisms, and we aren't there yet. So in resonance, we can add many arrows as we want. Okay? Was there now another way to do this? So let's pretend we don't have the red one. What do I have to do to my black structure to make it look like the purple structure? I can move the red bond here, which then will force the bottom black bond there. Why is that now like, oh, wait a second, why'd you do that? I moved the electrons from a bond to a bond. Okay. I just said earlier, bond to atom, atom to bond. That was it. Because I hadn't unhidden the bond-bond one. Why are we allowed to move bond to bond? Bond to bond is the same thing as moving from a bond to an atom, from an atom to a bond.
Just in one step?
It's just doing it in one step. Okay. Which do you want to do? Multiple steps or less steps? Everybody agrees with you. Okay? That's how we can also manipulate. The problem with that is, yes, it becomes challenging to see sometimes. Sometimes not. With practice, it becomes easier and easier and easier. Okay? So we have the black structure and the purple structure. Which one is the better Lewis structure? Black one because? No charge. Okay. Could I continue to do resonance with the purple structure? Okay. I could continue to move those electrons from here to, say, to here, right? What would the results of that arrow pushing look like? And yes, I did two arrows here. Didn't touch that double bond. A lone pair became a double bond here. And then the other double bond went here. Right? What happened to the negative charge? I don't accept it went away. It made our multiple bond. What happened to the positive charge? That one I'll kind of accept it went away. It went away because it gained electrons from a new pi bond. Is the black structure on either end of the page now identical? You look at those and you're like, those are exactly the same. There's no difference between them. No. What do you mean no? Okay, we could say there's a rotation, but rule 1 of resonance, it's pinned. You can't rotate it. So it's not a rotation, not a chair. The electrons shifted. Okay, the electrons are what moved, not the structure. Oh, well, electrons moved? What was the definition of resonance? Oh, yeah, electrons moving. There are multiple ways to draw this structure with the electron cloud. I maintain the same general format. I haven't introduced a higher energy state because it's charged. It's not charged. Okay. I now have 2 structures, 2 resonance structures for this compound. Which of those 2 is higher in energy? I already accidentally told you the answer, so if you were listening. They're equal. How do you know they're equal? Neither one of them is charged. Okay. Which means if I asked you to provide the resonance structures for the structure on the left, what are you going to draw? Structure on the right. Should you be drawing all the charged ones? That's where things snowball kind of somewhat uncontrollably. It depends on the question asked, how it's asked, and all sorts of other formatting issues within that. Okay? Unfortunately. Typically, no. You should not show the charged ones because they're unstable. Okay? They're not balanced. We don't want to show those. When we're drawing resonance, what we're trying to draw are the equal energy ones, not showing some other ones. Okay? Are those other structures still resonance structures? Yes, they just aren't as good. Okay? Would I want to look at those? Yes, good answer. Why? Depends what I'm looking for. In resonance, all I care about is the structure. Organic chemistry, we aren't just staring at structure all day. What are we doing with those structures? We react them. I want to know how that molecule can react in a different situation. I want to find within the molecule charge. If I look at the best Lewis structures, do I have charge? No, which means I've completely made it virtually impossible to determine anything about reactivity. But if I look at the first worst resonance structure, what do I now have? Charge, and I can now predict its chemistry. Okay? First worst is nobody's favorite statement to make, but we will continue to use it throughout the semester. Just kind of got to work with it. Okay, first worst, and then classmates always come up with some other phrase that I don't understand. Okay, but first worst is what I'll stick with until you correct me. Okay? So, we've now kind of addressed this best versus useful. Okay? Our best Lewis structures, and yes, this is particularly irritating, you need to satisfy the octet rule. That is first and foremost. Okay? Your best Lewis structure will have every atom with its octet satisfied. Okay? Rule number 2, minimize the charge. Even at the expense of exceeding the octet, even at the expense of putting a charge on an atom that you don't want to be charged. Are there other rules? Yes. Typically, we don't have to worry about them. It's really those first 2. So sulfate, we looked at an example for. Okay? We exceeded the octet to minimize charge. So we got a new compound here, CH3CO positive. Okay? See what you can come up with on drawing that. You'll notice that I am slightly different than most kind of Lewis structure representations. I'm actually trying to hint at the structure on the connectivity with how I've written that formula. Because I could have just as easily written it C2H3O. That would have been kind of confusing. Here, I very specifically switched the carbons around. Okay? So see if you can come up with a structure. Yeah, just give you a couple seconds. Information about getting to the structure. Okay, that's one of the things organic has as a kind of hands-down better thing than Gen Chem. Gen Chem, they just kind of, here's a formula, do whatever you want with it. Okay? We try to give you formulas that get you to a structure that we want you to evaluate because the structure is where the chemistry is at. Okay? We don't want you drawing 5 different structures with one formula because then it's very hard for us to ask a question about it. Okay? So here, we're saying we have a carbon with 3 hydrogens around it We have another carbon, and then we have, I'm going to draw it up here just because nobody else did that. Okay. Doesn't matter. Completely irrelevant. It's Lewis structure. Okay. So that's the basic skeletal arrangement. Okay. In Lewis structure, I need to know how many valence electrons go in. So carbon comes in with 4. There's 2 of them. Hydrogen comes in with 1. There's 3 of them. Oxygen comes in with 6. There's only 1 of them. Okay. The charge, so I spit on my screen. That didn't work so well. The charge is a +1, which means I need to subtract an electron. And I would have 8, 11, 17, -1 gets me 16 electrons. I would place my electrons around the oxygen first because it is the most electronegative. There's 8, 9, 10, 11, 12, 13, 14, 15, 16. Anywhere I have a pair of electrons, I can turn into a line, represent that bond. And I would end up with this as a structure. Okay.
Where did you get the
The -1 comes from the part that may have been difficult to see. Right there in the upper right-hand corner is positive. Okay. For the structure to become positive, what has to happen? It must lose an electron. What are we counting here? Electrons. That's why it's a -1.
So if it was a negative, you would add?
If it was a negative charge, I have to add an electron. Okay. So now what do? We've got the basic skeleton. I've added the electrons. Can't add any more. Now what? Satisfy octets. So this carbon, does it have its octet? This oxygen. Just to be exciting, this hydrogen. Yeah. Okay. How about this carbon? No. Okay. So what do we have to do? Share electrons. So I'll find an atom nearby that has excess electrons. Oh, I've got an oxygen right there. And I will shift those electrons now being between the atoms. Well, a pair of electrons between atoms is now a line representing a bond. Okay, cool. Does that oxygen have its octet? Yes. Whoops. Does that carbon have its octet? No. Okay. So let's fix that. What do we need to do? Share one more pair of electrons and I end up with triple bond. Okay. Now what do? Formal charge. And hopefully what you will find is the place for the formal charge is located on the oxygen. We end up with a formal positive charge. Several of you came up with this answer, and then I asked, well, isn't oxygen the second most electronegative element? And electronegativity is the ability to hold bonding electrons. And so since it's the most electronegative element in that set, what is it doing with all the bonding electrons? Holding them. Well, if it's holding them, what charge might we expect out of that? At least a partial negative. Okay? And instead we have the complete opposite. Okay? Does that make this structure wrong? No. Rule number 1, satisfy the octet. That is the Lewis structure. Is that the Lewis structure that is going to show how that molecule reacts? No. This may be the best Lewis structure. It's not the most useful. Oxygen, being the most electronegative, is going to do what to the bonding electrons? Take them. So it will take one of those bonding electrons, and what happens?
That would become, oxygen would become 0.
Oxygen becomes neutral. Okay, at least it's not positive. That's okay. But now what happens? The carbon becomes positive. When we look at this molecule, where's the reactive atom? The carbon. We end up looking at the most useful Lewis structure, which also happens to be the first worst Lewis structure. Okay? So it's not a question of just saying, well, I'm always going to draw the best. Okay? Unfortunately, the best doesn't get you the answer. Okay? The best may depend on the question asked. Okay? For those of you saying, well, isn't that some nuanced load of crap? Yes. Yes, it is. But that's how Lewis is defined. We have rules, you follow the rules when being asked for Lewis structure. When you're being asked to show how something reacts, Lewis structure guides us there, but it doesn't take us all the way. We actually have to take one step further and say, how does that balance out of whack? What's going to happen? That's how we end up with the useful structure in green. Yes, Henry. When we look at the purple structure,
That's green.
where's the charge? That's green. Thank you. The green structure, where's the charge? It's at the carbon.
He's asking why is the electron.
So why is the oxygen not considered our reactive site? If you are going to react, what are you going to react with? Okay. So in this room, I want you to react with something. Anything you want. Tell me what you're going to react with. It's an interesting question.
What did you?
The computer. Okay. Give me something else. Okay, react with a person. Anybody else want to venture a guess what else he could react with? The wall. Okay. And all of those things that you said to react with, did you say your hand, your ear, your foot? Why not? It was part of you. For the oxygen here, what did it react with? Part of itself. Is that a reaction? Not as we define it. The reaction is when a second molecule comes in to react. A second molecule cannot react with the oxygen. If the oxygen is positive, what does it need to react with? Something negative. So let's have something negative come in to react with the oxygen. That negative is now going to share electrons with the oxygen. What's the problem with that? We exceed the octet. Oxygen cannot react with something else because it would exceed the octet. So what will it do instead? React within itself, achieve its octet, its ideal charge, but at the expense of making something else reactive. So now when the negative comes in, it may say, oh, there's a positive carbon.
That's fine because it would accept.
And then that starts to satisfy the octet for carbon in that reaction. Exactly right. All right. Neat. Questions? At least I think it's neat. If you don't, talk to me in 6 months. Well, because then you'll think it's neat. You'll be like, God, please take me back to this. Okay. So the whole point of all of this Lewis structure and all this resonance stuff that you guys are doing within your homework is really to have you go through hundreds, if not thousands, of structures. Because what you will do at that point is pick up patterns. Organic chemistry is not about, well, how do I solve this question? It's about pattern recognition. You recognize the pattern, you match the pattern, there it is, done. There's not, oh, well, that had 2 and this one was a 2 and I now need to add the 2 but then divide because there was 2 numbers, divide by 2 and then add. No. Look for the patterns, match those patterns. Okay? To make things further simple, when we looked at the periodic table in organic chemistry, were we looking at the whole thing? No, we simplified that down, thankfully, to very few. Okay? This gets simplified even further. Boron, carbon, nitrogen, oxygen, halogens. Okay? Which, I mean, didn't simplify it that much more because halogen is the whole row, but okay. We're now looking at those elements and we want to be concerned about how those elements react. And when we go through and predict, we can look at our valence electrons. And then when we go through and draw out their Lewis structures, okay, we will notice that boron carries 3 bonds, carbon carries 4, nitrogen carries 3 and a lone pair of electrons, oxygen carries 2 bonds and 2 lone pairs, chlorine carries 1 bond and 3 lone pairs. Those are the neutral states. Why might we focus on the neutral states first? What is all chemistry striving for? Neutrality, okay, or stability. Okay? So if we know what those atoms are supposed to look like when they're neutral, okay, I can then look at it and say, that atom not going to react because it's in its neutral state. Okay, or less likely to react. Okay? But what happens in chemistry? Well, the whole point is to look at a reaction. Is looking at those Lewis structures going to help us? Probably not, because They're stable. None of them want to react. So what should we be looking for? How about their charge states? Okay. Boron's a weird exception, okay, largely because of that lack of an octet, and we'll come back to boron a couple times throughout the semester. Carbon, when it is positively charged, has 3 bonds. Nitrogen, 4 bonds. Oxygen, 3 bonds. Chlorine, 2 bonds. So recognizing those patterns and seeing when the charges show up, what their bond characteristics are, what the lone pairs are, having that memorized can now shortcut all of that Lewis structure stuff that you're messing with now. And you're like, God, this is so hard. I wish there was a shorter way. There is. Memorize a bunch of common patterns. Once you have the patterns memorized, you're good to go. How many people can memorize the patterns? Very few of us. What do the rest of us have to do? Draw Lewis structures. Okay? So these are our basic systems and how we build. When we move to negative charges, we've got similar patterns coming out of them. Okay? And a lot of it is just a question of either adding more electrons or removing electrons and just changing those states. Within these, do I make any mention of multiple bonds? No. Could I have a carbon with 2 double bonds? Yeah, it has a total of 4 bonds. Okay? And in that state, is it neutral? Yes. It still matches that drawing. It's not saying that I have 4 single bonds. It's saying I have 4 total bonds. Okay? So then the next part, will the shape of the atom or molecule change the interaction?
Yes.
Yes. Okay? If I happen to have this interaction with you, probably like, oh yeah, hi Mike, how's it going? As opposed to, say, we're going to get a slightly different interaction, even though it's the same object. I didn't rip fingers off, but I changed how they were arranged. And now all of a sudden we get a slightly different interaction. Oh, interesting. So does the shape have an effect? Yes. Which means, what do we need to know? The shape. How do we predict shapes? No, almost. That was a really nice lead-in that then got botched. Slid this slide around a couple of different places. Formal charge, we talked about formal charge and how to evaluate it. Okay? If we take a look at these 2 structures, we could go through and assign formal charge, and what we would notice is that we only have a -2, or 2 minus charges show up for the sulfate that we accepted as our best Lewis structure. And the one that we said was bad had lots of charge. Every single atom had a formal charge. Okay. What if we looked at the oxidation state? And now everybody goes, well, oxidation? Wasn't that like single replacement and electrochemistry and all that stuff I really wanted to forget about? The oxidation state won't change. Okay. So the oxidation state actually doesn't help us draw a Lewis structure because it doesn't allow us to look at bond patterns because it really ignores the bond patterns and just says what atoms are present. How do those atoms transfer electrons between each other? So while the oxidation state can be a helpful tool, it is not one that we will typically use. Okay? If you want to calculate it, the textbook explains how to go through and do it. I personally find it a little bit confusing. If anybody care to look at the oxidation state?
No.
Thank you. So now let's skip to the nice segue, VSEPR. Okay. We want to be able to predict our shape from our structure. Lewis structure says nothing about shape. We have to interpret our Lewis structure to come up with shape. Okay, so one of the things that we start to assume, or make correct assumptions about, is that electrons, being the same charge, and the largest part of our atom, okay, not mass, but size, okay, are going to repel away from each other. Lewis fails horribly at this. Okay? Because our classic example, that's a C, by the way. Methane, CH4, what is the bond angle between those 2?
109.
What is the bond angle up here according to Lewis? 90. Bond angle there. Okay. Which we might say, well, that's kind of the point, because all the hydrogens are the same, which means I would expect the same bond angle across the board. Well, they're all 90, aren't they? No, good, no. What's the no? What's the bond angle? 180. Lewis structure fails its shape. Okay? All Lewis structure is trying to do is take a three-dimensional object and smash it as flat as possible and roughly interpret it. Okay? So Lewis fails. What do we need to move to? That's our valence shell electron pair repulsion theory. Okay? So our bonds or our electron orbitals will move away from each other to achieve the maximal area possible, okay, the maximum space. That produces electron pair geometries, okay, where we have linear, trigonal planar, tetrahedral, followed by what? Nobody? Don't worry about it, because our periodic table, as far as organic chemistry ends, is that first row, which gets us up to tetrahedral. We don't have to worry about all the other ones. Thank God. Right? So what we're looking at is our electron geometries here. Right? So that gets us to those shapes. We have tetrahedral, trigonal planar, and linear. Tetrahedral is kind of our sweet spot where almost everything exists. Okay? What happens if we then look at a couple examples? Say CH4. Come on. I'm yelling at my pen, not you. How many groups of electrons are around our central atom? 4. Electron, come on. Electrons, 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 electrons. We get 4 groups. That gets us to the tetrahedral shape. What happens when we go to NH3? Hopefully you'll come up with that Lewis structure relatively quickly, and we go through and decide how many electron groups are there. Are there electrons there? What is our electron shape? Tetrahedral. So I would then predict that the bond angles in methane and ammonia to be the exact same. Are they? No. Why not? The lone pair is different than a bonding pair. That's why we call it a lone pair and a bonding pair. They get different names, so they have different features. That feature changes the geometry within our molecule, which means I can't refer to this as tetrahedral. So I'll call it trigonal planar. No, I still have a group of electrons. Trigonal planar is only 3 groups of electrons. There's a third. Okay? So what do I need to now invent? Okay. Another reference, where I'm now looking, instead of at the electron groups, I'm going to be looking at the relationship between bonding electron groups and non-bonding electron groups. And I would refer to ammonia's shape as trigonal pyramidal. Okay? So that would scale out to some multiple groups, depending on whether we have lone pairs or bonds. So this is now our home for all of our possible shapes. Okay? I just hear sick. Okay. There are some other slight variations, but for the most part, the names are already there. Okay? So the big shape summary, if you need help with it, this portions everything out. The tutoring center also has an equivalent version of this. You're drawing out your Lewis structure, you evaluate groups of electrons, you come up with bonds, non-bonds, and all that fun stuff. Hopefully, vaguely sounds familiar. I'll say that was a yes. So how do we then apply this? Okay, if we look at methane, that was our CH4, we already saw that. Okay. Well, now we got a tricky thing. So now I'm bringing in nomenclature into this, my least favorite subject. Okay. Cyclobutane. Let's break that name down. Cyclo sounds like cyclic, okay, or a circle. That's a circle. Not sir. Sird. Sired. What else do we have within the name? We have but and we have ane. Notice the ane shows up the same in both. What is the ane referring to? Single bonds. Okay. So our structure will only have single bonds. A guess is a guess, that's fine. What does the but mean? We'll call it but. Means 4. How do we know that?
You memorized it.
You memorized it. Guess what nomenclature is? A bunch of memorization. Okay. So my story on nomenclature, number 1, first time I took organic chemistry, anybody want to guess the grade? F was a bit excessive. It was a W, because I was doing so poorly I withdrew. Okay. Second time, B+. Okay. And second quarter, B+. That one was fun. There was 1,000 points, and I got 890 points. Yeah. What was the other 100 points in that class? Nomenclature. Second time I took organic chemistry, I went through and looked at the subject and said, okay, what parts do I think are important, what parts aren't? Nomenclature was one of those parts that I said, nope, don't care. Not going to worry about it. So every time it showed up on the test, left it blank. Okay. Organic chemistry has a lot of material in it. You are going to have gaps. The question is, do you choose your gap, or are you going to let the gap choose you? Okay. It wasn't quite as deep as I had intended. I picked my gap to be nomenclature, and because of that, I pretty much lost an A. Okay? You have to decide where your gap is going to be, pick your battles, and do what you can within it. You can try and be a jack of all trades and try and get bits and pieces of everything down, and that could work. You could also just be that awesome. That's cool too. Okay? Just don't rub my face in it. Okay? So when it comes to nomenclature, there are individual chapters set out in our textbook referring to how to name. Read those chapters. Okay? I will try my best to bring nomenclature in at kind of random spots like this where we then have to evaluate it. We'll also have kind of a nomenclature lecture where we look at bits and pieces, but it is not divided out as well as, say, a different textbook does, because in the different textbooks they do it based off of functional group. Our textbook just says nomenclature sucks, here's a bunch of chapters to talk about it. Covers all nomenclature, okay, as opposed to dividing the pain across 50 chapters. Okay. Just like a Band-Aid. Okay? So, but means 4. What does meth mean?
Bad.
Methane, 1 carbon. F, 2 prop, 3 but, 4 pent, 5 hex, 6 hept.
7.
I jumped ahead. Non, 9. Ooh, oct. Good job. Okay. So those are our basic building blocks of looking at how many carbons are in our structure. We need that information when we're going from the name down to our structure and from the structure back to the name. Okay. So in this case, I have 4 what? Carbons, because this is organic chemistry. Yeah. And it's arranged in a circle. So, what is that going to look like? Okay, and we can say, oh, that's a circle. We have a square. How many electron groups around the carbons in methane? Electron groups. 4. How many electron groups around the carbons in cyclobutane? 4. What is the bond angle, or what is the shape in methane? Tetrahedral. In cyclobutane, each of our carbons should have what shape? Tetrahedral. One of the things I didn't mention, which I'm kind of relying on you to have remembered, tetrahedral has what bond angle? 109.5. What was the shape I just drew for the cyclobutane? A square. What is the bond angle in a square? 90. Is that 109.5? No. So sometimes our structures will be forced into unnatural bond angles. We just have to be aware of that. And that allows us to then think something about reactivity. If you are being forced to do something, you are probably going to fight back. What do you expect to happen if we say broke one of those bonds? It's going to fly open very violently and react very quickly, okay? Because it has now got a bunch of strain where it does not want to be at that angle. So it ends up being more reactive. So we can start to predict something about reactivity, again, based off of shape. Okay? Chloromethane. Another nomenclature. So we have the methane, so we're probably looking at, again, methane, right? But then I'm missing the chloro part. What does chloro sound like? Chlorine. So I need to put chlorine in here. Oh, that didn't work. That exceeded the octet. Okay. So I'll just put it over here. Well, that didn't work either. We'll remove one of the hydrogens. Hydrogen is by default added to pretty much just satisfy any missing sections. Okay? So when we're looking at our name, the chloro needs to go in, and it needs to be attached to one carbon. What else is attached to the carbon? Anything else that doesn't affect the shape or the structure or the formula, which will be hydrogens. Okay, so we end up with chloromethane.
Hydrogens never affect the shape?
Not shape. Shape was a bad word. So ignore shape. Hydrogens don't really affect the reactivity. What is the bond angle now between those hydrogens? Iron 109.5. Why are you saying 109.5? The carbon has 4 groups, which means tetrahedral, which means 109.5. Okay. The reason we're at 109.5 is because all of those groups are equal. Are all of those groups equal? No. Chlorine is inherently different than hydrogen. That's why we call it chlorine and not hydrogen. How is chlorine different from hydrogen? It's bigger. What do you mean by bigger? I'll agree with that. More electrons. Okay? The protons we don't care about, that's mass. We care about size. So electrons. It has more electrons. If it has more electrons, what is it going to start to do? It's then going to push harder against the other atoms, and we start to see the shape change the bond angles. Ooh, tricky. Okay? So we have to be aware how those different atoms or different atom substitutions will change our shape. Does it change it a lot? No. Does it change it significantly? Yes. Okay? How about a methyl carbocation? Methyl means one carbon. This gets a little bit trickier. We're saying methyl, YL, as opposed to methane. What does the YL mean? It's a functional group. It's a piece of something more important. Okay? When we looked at methane, well, there wasn't anything else, so it's just methane. Okay? When we're looking at methyl, we're now saying that one carbon is piece of something more important. What is the something that is more important? What does that say? Carbocation, meaning a positive carbon. So what does that mean? Where's my positive carbon? Okay, would there be another carbon? How many carbons are there now? 2. How do we name 2 carbons? Ethyl. What is the name? Methyl. So 2 carbons is wrong. Where's the positive charge? It's on that single carbon. Okay. Carbon's supposed to have 4 groups of electrons. Will it have 4 groups this time? No, because one of them is a positive charge. So what are the other 3? Hydrogens. What is the shape? Trigonal planar. Okay? It can't be tetrahedral because it does not have 4 groups of electrons. It only has 3, and then it has the 4th thing which has no electrons, so by definition cannot be a group of electrons. So it can't fit in the tetrahedral category, which means it also can't be trigonal pyramidal. So that puts it in the trigonal planar situation, and that's all we've got. So it is now a flat molecule.
What was the other one you said? Trigonal
Pyramidal
pyramidal?
or pyramidal. Pyramidal. You can come up with different ways to say it. And you can't laugh at me when you say something, or when I say something funny, but I can laugh at you. Bromomethane. This is the last one we'll look at, I promise. Bromine, carbon. Here's the challenging one. Bond angle here, our blue bond angle versus our green bond angle. Which one is bigger?
Blue because bromine is
Has nothing to do with electronegativity.
it's more bigger.
Bromine is bigger. Yes, I agree with that statement.
Pushes more on the.
Yeah, it pushes the hydrogen.
Okay, so we're saying the bromine being bigger is going to push more on the hydrogens, so that angle then shrinks a little bit, right?
Yeah.
Everybody agree with that?
Yeah.
By bromine being bigger, what else is bigger? Carbon doesn't change.
The bond distance.
The bond length. So yes, it gets bigger, but it also gets further from the carbon. As it gets further from the carbon, what happens? The bond angle actually opens up. Yeah, love that one.
So wait,
That's one of my favorites.
the green.
The green one is actually larger bond angle. Yep, very counterintuitive. But the green one has a larger bond angle, which we will discover when we look at reactivity. Okay? So drawing organic molecules. Draw the structure of the compound with this formula, C5H12. No more than 30 seconds. Everybody have it yet? No? Okay, sorry, I'm just checking. Just forgot I was recording that time. So. There we go, that's our 30 seconds. Tough. So how many people came up with this for an answer?
What's the name? It's the shape as well.
Anybody get that answer?
No.
So you all failed. What's the problem?
Formula.
Formula. Formulas suck. Do not ever give me a freaking formula. Okay? Formulas are pretty much utterly useless. More than likely what you all came up with was the nice straight line. Because why? It's the easiest, yeah. Okay. So one of the problems that you might see pop up in the homework was here's a formula, provide all of the structures that represent this formula. It is supposed to be an irritating, frustrating question because it's supposed to get you to realize that formulas are horrible. And it is very hard to find all of the structures. Okay? So when we start with a formula, we can start to back away from that and go straight to maybe a Lewis structure. The Lewis structure is looking at the actual connectivity between all of those, and that can simplify things. Okay? We could also go through and provide a structural formula. Sweet, and that was the one I drew. Okay? The structural formula now reveals a little bit more information about what we're expecting for the connectivity of those groups. Okay? Notice within this I have CH3 parentheses 2, meaning I need 2 CH3s. Those 2 CH3s are connected to the very next atom in that list, the carbon. That carbon needs to have 4 things attached to it. It's already got the 2 CH3s, so I list the next one, hydrogen, and the next one, carbon. Okay. How many of you like looking at a structural formula? Oh, wow. Okay. Better than the formula. Okay, yes, that's true. I'll accept that one. Okay. The issue with the structural formula is that hides some of the chemistry. It can make it difficult to find atoms, particularly if you have a very large structure. Is it something you are required to do? Yes. Get used to it. Keep working with it. You will see it constantly. Why do we use structural formulas? Gives us a little bit more information about structure. Why not just draw the Lewis structure? We could go with takes up more space. Think about technology. What did we use to present our data? History. First, by pen and paper. Well, pen and paper is easier to draw it by hand, so we stuck with drawing by hand. And then we came up with this fancy new tool known as printed materials. And in printed materials, we only had certain letters that we could bring in, and we couldn't bring in the different shapes. And we had typewriters, okay? And a typewriter works perfectly well in the full page two-dimensional space, right? No, it only goes in straight lines, which then means we need to come up with a way to convert our Lewis structure into a straight line format. Okay? Why are we still using it? Because we still use computers, and technology hasn't quite gotten to the point where we can stop using these structural formulas. Okay? You will also see them sometimes referred to as a condensed formula. There are a couple other versions that can pop up out of this. We get the VSEPR structure. VSEPR was telling us what?
Structure in a three-dimensional space.
Three-dimensional space. Okay? So it got us something to do with bond angles. So instead of drawing out, yes, that was me growling. I'm not going to show all the freaking hydrogens. I'll just show the bonds. Okay? Instead of drawing that all out, what I might go through and do is draw something. That was me growling again, but differently. Okay? With all our hydrogens. Okay? Do I know where those hydrogens are aimed?
Yeah.
What is the bond angle between the carbons? 109.5. What I'm going to do is organize or orient the molecule, my carbon backbone, to all be in the plane of the paper. Because in the plane of the paper, I can use solid lines. But if that's the case, what happens to the hydrogens on that tail end carbon? Are they all going to be in the plane of the paper? No, one of them will be. What about the other two? Well, your hand works as kind of a pseudo-tetrahedron, okay, where my wrist is the top atom. Okay, the top atom and my thumb are in the plane of the paper. Okay, it's the vertical line running like the front wall. What about my index finger?
Forward.
It's coming forward at you. What about my middle finger?
Pointing down away.
Down and away. Okay? I want to add information to my drawing to represent this as best I can. To do so, I will then change this to being a wedge. Okay? That wedge appears to be getting kind of bigger. It's starting the carbon, it's growing out bigger and bigger and bigger. What happens when things get closer and closer and closer to you? They get bigger. Guess what we're showing with the wedge? It's getting closer to you. What are we doing with the back one? We're showing a dashed line. Okay? And that's because it's getting further and further away from you. See, mirages, they have that kind of shimmery effect because of all the dashed lines in the way. Come on, that was kind of funny. Watch the video again. So we can add something about three-dimensional characteristics by using wedges and dashes and now showing some bond angles roughly approximated from our Lewis structure. We can shift to line angle and VSEPR, okay, which is very similar to our VSEPR, except in that case where we end up drawing it is starting to make some abbreviations. The abbreviation that we end up making, what's the first abbreviation I'm making? I've stopped drawing the carbons. Okay, the carbons are still there, but the carbons become implied. They are implied at what location? At every point, which can be an intersection, but I would also argue is not. That blue dot, is that an intersection? That's a little bit of a gray area. I would call that a point. So every point is defined as a carbon. Okay? The VSEPR is then layering on and adding some wedges and dashes showing where everything is located around our carbon skeleton. What happens when we move to line angle abbreviated? We've now simplified it even further. Okay? Every point is defined as a carbon, and we've also now stopped showing hydrogens. Okay? Why? Because it was really tedious to draw all the hydrogens. So we now assume that the hydrogens will fill in the missing octet for every carbon. Okay? We're going to go, well, that's not that bad, until you start doing chemical reactions, and then you forget that you had hydrogens. Okay? So remember the abbreviations within this, which hopefully gets us to our simplifications, which is a pretty good place to stop. Largely, we are concerned with 8 elements: hydrogen, boron, carbon, nitrogen, oxygen, and the halogens. Okay? We use simplified shapes and hybridizations. Okay? We haven't got to hybridizations yet, but we will talk about that. And then our abbreviated drawings. Assume every point is a carbon unless otherwise specified. So if I just draw a line, what is my formula? Let's not do that yet. I lied. Let's get through step 2. Hydrogens will be implied to carbon to satisfy the octet. Notice to carbon is capitalized. Do we imply hydrogens to any other element? No, only to carbon. What is the formula for that line? C2H6. Okay? So we get a lot of stuff implied out of our structures. Okay? The next big parts are really the things that we don't imply, and we have to be careful with these. Charges are never, ever, ever implied. Okay? They will always be shown. Okay? Why do we have to show them? Because we implied hydrogens. Okay? We can only imply one thing. We can't imply multiple things. Okay? The next part, nitrogen, or all of your nitrogens, which is always a fun word to say. Oxygen, C, and our halogens often have implied non-bonding electrons. Okay? This is particularly irritating, and there's nothing that you can do about it. Okay? I will try my best within first semester that if I draw a nitrogen, oxygen, or a halogen, to always draw the lone pairs. Okay? I will fail. Right? That's just going to happen. Okay? But I will always try to show them. Why do we need to show them? In resonance, what did we move? Electrons. What if you've implied the electrons? It becomes very difficult to see your resonance. Okay? Because you are learning the material, you're having problems with that, you need to see those so that you can help get through the resonance parts of it and deal with that structure. Okay? So again, I will try to remember to draw that. Your textbook, I'm sure, tried to do that, and they failed pretty utterly too. Okay? So it's going to happen. Just kind of watch out for that. Those are our big simplifications. We will pick up with our functionality, which ultimately gets us into reactivity and intermolecular forces on Monday.